And welcome to HoTT. Our speaker today is Carlo Angiuli, who will speak about internalizing representation independence with univalence. So, Carlo, the stage and the moment are all yours.
Great, thank you, Chris. Okay, so today I'm going to be talking about some work that was recently at Popple. You can see a link to the paper here. Because it was kind of geared toward a CS audience, I want to spend a lot of time today kind of giving the motivation of the work. And I think that you'll appreciate the motivation because it's related to formalization and making formalization work better. But so I'll start there. Then I'll give a bit of background on cubical type theory, which you're probably sick of hearing by now, but there'll just be very little bit of that, and on the structure identity principle. And then at the end, I'll talk about our contribution, which is a sort of relational take on the structure identity principle. And as we like to say in the seminar, everything in the talk is formalized. It's in Cubical Agda. If you wandered in here and you know everything about representation independence and nothing about homotopy type theory, there's another shorter version of this talk that maybe is better suited for your background. But anyway, I'm glad you're here. Okay, so what is representation independence? Well, I think Mitchell put it really well when he said, one purpose of type checking in programming languages is to guarantee a degree of representation independence. Programs should not depend on the way moduli spaces, stacks, are represented, only on the behavior of stacks with respect to push and pop operations. Okay, Mike's laughing, right? A different kind of stack. So basically, this is a sort of principle of modularity. And let me give you an example of one of the typical instances of representation independence. So a queue is a data structure, which you can kind of think of as a British queue. It's like a line of natural numbers in this case. So there's an empty queue or empty line. If you have a queue, you can put a natural number on the back of the line. And if you have a queue, you can take a natural number from the front of the line. Now here, maybe q times n just means 1 plus q times n. So maybe the list is empty, in which case dq fails, but otherwise you get the rest of the queue and you get the first natural number that was in line. Okay, so there's a very simple way to implement a queue, and that's using a list. So you can say that the empty queue is the empty list, and queuing is just the same as cons. And to dequeue, you have to take the last element off of the list. So here I have a picture at the bottom here where the arrow is kind of indicating the direction that the list is facing. You're enqueuing on the front, and you're dequeuing off the back. The problem with that representation is that dequeue is very inefficient, because to write this last function, you have to process the entire list, recur down it until you find the last element of the list, and the amount of time that takes is proportional to how many things are in the queue. So there's another way that you can represent queues, which is as a pair of lists, and this representation is called a batched queue. And the way that it works is you have two queues, one representing the first part of the queue forward, and then the rest representing the rest of the queue, but backward. So the way you enqueue is you con something onto the first list, and the way you dequeue is you pull the first thing off the con cell on the second list. So both enqueue and dequeue are constant time, except that sometimes you're trying to dequeue and there's nothing in the second list. And if that's the case, then you take the first list and you flip it, and you make that the new second list. So basically, enqueue and dequeue are always constant time, except once in a while you have to flip the first list to make it the new second list. And you can actually show that on average, the dequeue still ends up taking only a constant amount of time. Okay, you don't have to understand this example perfectly, but does that kind of make sense? Feel free to interrupt me, especially in the first part of the talk, with any questions. Okay, so the problem So you might be thinking univalence or something like that. The problem is that list queues and batch queues are not isomorphic. So there is a correspondence between these representations. But for example, if you think of a queue with 2 elements, there are actually 3 different ways it can be represented as a batch queue, depending on where the kind of split in the middle of the queue takes place. So while the list queue sort of is the normal form in some sense of a logical queue, a batch queue is kind of unconstrained. There are a lot of ways that a single logical queue can be represented. So the way that representation independence is usually phrased is something like we say that if we have 2 implementations of some interface, like the interface of queues, then they're interchangeable whenever there's a structure preserving correspondence between those 2 implementations. And the details of these theorems differ slightly between programming languages, but just to give you an idea of what I mean, in this case, if we have 2 queues A and B, and we have some sort of relation between the carriers, in this case, list versus list times list, then to be structure preserving means that the relation relates to 2 empty queues, and that if 2 queues are related, then n queuing preserves that relation. And if 2 queues are related, if you dequeue, either both of them were empty or both of them return the same thing off the front, and the rest of the queue is also related. Now, we usually prove this kind of theorem as a sort of consequence of another meta theorem called parametricity. So the classic example in the literature is that in system F, which is sort of a simply typed lambda calculus with an impredicative type quantification, we can prove a theorem called parametricity, and then as a result, a theorem like this representation independence theorem at the top of this slide is a consequence of that. And the reason why we want to do this is that list queues are easier to reason about because the implementation is very simple, but batch queues are more efficient. So we kind of get the best of both worlds, where we get to reason about the nicer implementation, but then use the better implementation. And of course, there are plenty of examples that are much more complicated than batch queues.
Sorry, I didn't get why the statement of the theorem is what's the definition of observationally equivalent?
Right. So this is something from PL that I don't really want to get into, but basically what it means is that if you have any program and you swap occurrences of A for occurrences of B, then it will compute the same result.
Oh, okay.
Yeah. But I won't be using that in this talk. Okay. So a natural question. So usually these programming languages, something like System F or ML, they don't have types that can express that a function does the correct thing. But in dependent type theory, a natural question is, can we get these sort of consequences of parametricity? Can we get a representation independence theorem internally? And there actually is a lot of work on doing this in dependent type theory that mostly falls into 2 different camps. So there are these so-called parametricity translations, which usually say something like, if I have some kind of pure type system, then there's some other pure type system that's powerful enough to construct the sort of parametricity model of the first type theory. And then we can specify the model as a sort of syntactic translation. So in the second theory, you kind of get the representation independence theorems about the first theory. The other kind of thing you can do is called internal parametricity. And that is really analogous to univalence. So if you think of univalence as internalizing the fact that everything respects equivalence, then internal parametricity is internalizing the fact that everything respects structure preserving relations. And there's some early work on that called type theory in color, which actually had a lot of influence back and forth with the first cubical type theories. It's a lot like the BCH cubical model of type theory. And more recently, that sort of internal parametricity has been combined with sort of full cubical type theory by Cavallo and Harper. Now, this work on internalizing parametricity, for the most part, was not actually motivated by the sort of Q example, but instead by mechanization of mathematics, and especially in the Coq proof assistant. So the reason is that, once again, often the representation that is easiest to reason about is not the representation that's the most efficient. So, if you think about the natural numbers, they're really nice. The 0 or successor Peano natural numbers, they're really nice because you the induction principle is mathematical induction. But of course, they're very slow to compute with. You'd rather compute with, well, we usually say binary numbers as our example, but that's actually a bad example. A better example would be, machine integers, which are really fast. And this does come up in practice. For example, there's a paper mechanizing the proof that the zeta function at 3 is irrational. And to do that required computing some bounds on polynomials. And to do that, these were just concrete computations, but the integers were about 4,000 digits. So imagine trying to do that with successor of successor of successor, that it doesn't really work very well. But if you do it with a machine integers, it's very fast. So there are a lot of examples like this. I mean, also matrices versus sparse matrices and so forth. And once again, all of these examples on the slide, they're not actually isomorphic. So the natural numbers are not actually isomorphic to machine integers. There are a lot more natural numbers. In sparse representations, there are a lot of different ways you can make something sparse. So once again, it's not an isomorphism, just like in the Q example. Right, so building on this sort of work, there are kind of two main solutions in the context of dependent type theory for this sort of proof reuse problem. One of them is called coquille, which I guess is a funny joke if you speak French. And there they use a parametricity translation to sort of get representation independence theorems to transfer. In fact, all of the examples on this slide are things that they do in coquille. But there's for technical reasons, I don't really want to get into, it can't actually handle large eliminations. So you can't transfer things that use large eliminations. It still handles a lot of cases. But more recently, there's something called univalent parametricity, which uses univalence to get a sort of representation independence. So this does, of course, handle dependently typed goals. But the problem is that you can only apply univalence to equivalences. And once again, a lot of the things I'd really like to apply this sort of idea to are not actually equivalences, like all the things on the previous slide. So that's basically where our work fits in. And we're trying to bridge the gap between these two approaches. So use univalence in higher inductive types so that we can sort of handle dependency and all the features of type theory, but on the other hand, be able to apply it to things that aren't isomorphic. Does that make sense? That's the end of my intro, so this is a great time for questions. Okay. All right, so just a really quick overview of Cubical Agda. So Cubical Agda, if you have a new enough version of Agda, you can just use the cubical flag and get cubical type theory. It's pretty cool. You basically get CCHM or De Morgan cubical type theory. There's some caveats here. For example, it's the sort of the version of CCHM that's in this paper I cited here that handles hits and so on. And there's also a nice standard library for Cubical Agda that's in development here at the link that is on the slide. And everything that we did in this paper is part of that library. So the core idea of cubical type theory is that we define the propositional equality connective in terms of a primitive interval. So we add this interval I. It has two elements, I0 and I1, that represent the endpoints of the interval. Now in Cubical Agda, you also get this meet and join and involution on the interval, but we don't need that in this talk. And using the interval, we have these path types. So the type of paths or qualities between A0 and A1 in the type A are, you can really think of them exactly just as functions from I to A, such that on I0, they're equal to A0, and on I1, they're equal to A1. So using these path types, we can, for example, define a reflexive path. Reflexive path at X is just a constant function on the interval that always returns X. And without univalence or anything else, we get function extensionality. So if you have sort of a pointwise family of paths, you can turn that into a path in the function space just by flipping the order of two arguments. And what's really nice about this is, first of all, it doesn't use univalence. And second of all, this is actually a definitional isomorphism, because if you flip twice, you're back where you started. So you can sort of use funxt as much as you want, and it never bites you. Path types are actually a special case of the real primitive, which are dependent paths, which are just like path overs in HoTT. So these are just dependent functions out of the interval. And the reason I say they're path overs is because a family of types indexed by the interval is like a path in the universe, and the two endpoints are lying in different types that are, correlated by that path. So using this sort of primitive notion of path over, this is also quite nice because, for example, if you look at trying to characterize equality in a sigma type. So if you have two elements X and Y of a sigma type, you can prove that the paths between X and Y are equivalent to the paths between their first components and coupled with the paths between their second components lying over the first one. And again, I mean, it's not surprising that that's true, but the reason I put the proof on the slide is that you can see that the maps back and forth are basically just swapping the order of pairing or projection with abstraction of the interval. And again, this is a definitional isomorphism. You see that the round trip laws are just REFL. So again, it works pretty nicely. Now, I'm not going to bore you with the details of the con operations or the glue types, which you may have heard of, but there's a bunch of technical details, and the upshot is they give us a computational justification for, well, there's a primitive called transport that turns a path into an equivalence. It has an inverse, we usually call UA, and if you transport over UA, it applies the function up to a path. But maybe other than path overs and function extensionality, maybe the nicest feature of cubical type theory is you get a very nice notion of higher inductive type, where you have you can do pattern matching on them, and the eliminator will compute on the path constructors. So here's the data type declaration for the propositional truncation. So there's an inclusion of A into the propositional truncation of A, and then the squash constructor says that for any two elements of the propositional truncation, there's a path between them. Now, if you remember that what a path means is just it's a function out of the interval, so you can really, if you unfold squash, you can think of it as not a two-argument constructor, but a three-argument constructor, the third argument being an element of the interval. And when you apply it to 0 or 1, it is exactly the same as X or Y. And when you pattern match, here I'm pattern matching on propositional truncation of A, you do apply to squash X, Y, I, and there's just this sort of invisible side condition on this last clause where you have to make sure that this clause respects the two equations of what squash does on 0 and 1. If you don't do that, then this definition doesn't type check. The last hit that I'll really be using a lot in this talk is the set quotient. It looks like this, but the one thing I want to point out is that one thing that's really nice, sort of from the perspective of me, about the set quotients in HoTT and in Cubical Agda, of course, is that if you're quotienting by an H-prob valued equivalence relation, then from a path in the quotient, you can actually get back out the evidence that the relation holds. And this ends up playing an important role later in this talk. Okay, that's enough about Agda. So what is the structure identity principle? Well, it's this kind of informal principle in some sense, which says that equalities of structured types are equivalent to structure preserving equivalences. Now, the reason I say that's kind of informal, that looks pretty formal to me, the problem is that you have to define what all of the words in this theorem mean. So in particular, you have to say, what is a structure preserving equivalence? And in fact, what is a structure? What is a structured type? And this has been treated in a whole bunch of ways. This is, not our work, but these different treatments differ in a few ways. So an example of how they differ is that some of these actually define what it means to be a structure preserving function, and then restrict to the ones of those that are equivalences. But what we do is we just directly define conditions on an equivalence to say what it means to be structure preserving. And I'll tell you how we do that in just a second. But our formalization of the SIP is very close to Martin's. He has some very nice lecture notes, by the way, called Introduction to Univalent Foundations of Mathematics with Agda. I recommend them. Even if you're an expert, you can learn something. So basically, we're doing what he did, but some of the definitions are tweaked so that they work better in the cubical setting. So this is how it works. So a structure, we just formalize this notion as a function from the universe to itself. And an S-structured type is a carrier type along with a structure on that carrier. So for example, if we look at monoids, a monoid is a type coupled with an identity element and a multiplication, and then maybe some axioms. And I'll get to how axioms work in a couple slides. But then, okay, so S-structured type, if we have two S-structured types, A and B, and we have an equivalence between their carriers, first of A and first of B, then we'll pair with S this notion of being S-structured, and I'll write that iota. So iota is just sort of a predicate on equivalences between carriers that says what it means for this equivalence to be preserving the S structure. And you can define this however you want, but we'll say that one of these notions, iota, is univalent if it has this kind of funny looking property that iota holding is equivalent to some path over. And I'll explain where that path over is coming from in just a moment. But let me sort of give you an example first. So let's look at the pointed structure, which is the identity function. And the reason I call it the pointed structure is that if you have a type with a pointed structure on it, that's just having a pointed type, a type with an element of that type. So we're going to say that a equivalence between A and B is pointed if it sends A naught to B naught. Okay, makes sense. Up to a path, of course. Now, we can prove that this notion of pointed equivalence is univalent. And to do that, just recapping the definition, we have to say that iota holds of F exactly when this path over is true. But if you look at this path over, well, you can always turn a path over into a homogeneous path just by transporting one of the endpoints. And if you do that, then you see that transporting across UA is the same as applying the function. So this condition is exactly the same as saying that F of A naught is B naught. But that's exactly how we defined iota. So this iota is in fact univalent. Then we prove that the natural notion of S-structured equivalence, the sort of one you expect, is univalent for any structures built out of this grammar. Okay, and one nice thing that we did was that we wrote some sort of macros in Agda that use reflection to automatically match this grammar. So you don't have to build up the sort of proof that, or you don't have to build up the notion of structured equivalence or the proof that that notion is univalent using combinators. You just can simply pass in the actual function that defines the structure, and the macro will spit out these things. Then a corollary of, so this is kind of the real theorem. because you have to define what it means to be S-structured and check that it's univalent. And once you've done that, the structure identity principle is basically just a trivial corollary. So you can think of it as saying, for the notions of S-structure, for the S-structures that were on the previous slide, and for the notions of S-structured equivalence that we defined, then having a path between two S-structured types A and B is equivalent to having a equivalence between their carriers that is S-structured in the sense of iota. Okay, and the proof is actually very simple. Say, okay, well, an equality in a sigma type, that is the same as an equality of their first components and an equality of their second components. But an equality of their first components is a path in the universe, which is an equivalence. So if we rewrite by univalence, we see that this is the same as having an equivalence between the carriers and path over that equivalence. And then you see that the second component of the sigma type, this path P expression, this is the fact that iota is univalent is precisely the statement that this path P expression is the same as iota holding. So if you, so by the fact that iota is univalent, we get the rest of the SIP here at the bottom of the slide. Okay, what about axioms? So the grammar just includes kind of the operations, but not the axioms. And the way that we can add axioms is basically that if you have some sort of predicate on S-structured types that is an H-prop, then you can define the notion of being S-structured and also satisfying the axioms, okay, just as a sigma type in the way that you think. And because the axioms are an H-prop, it doesn't affect the equality of the sort of augmented sigma type. So it's very easy to show that if S and iota are univalent and the axioms are H-prop valued, then the S structures satisfying the axioms are also univalent. Now, so using this sort of decomposition, we can define all the sort of usual algebraic structures in our setting. So you break them up where you say, I have a raw monoid, which is just having an identity element and a multiplication. And then the axioms are some property of a raw monoid that says that it's associative and unital. But for these associative and unital conditions to be an H-prop, you have to require that the carrier is an H set. So if you are an expert in the SIP and you were getting kind of itchy that I didn't say anything about H level yet, this is where it comes in. The theorem over here has nothing to do with H level, but over here, if you want to add axioms, basically whenever you add axioms, the first axiom you have to add is that the carrier is an H set. Okay.
Carlo, can you explain the theorem on slide 21 a little bit more?
Yes. So, okay. So you understand what I mean by this grammar?
Well, I can't really absorb it that quickly. So maybe you should.
Okay. Right. So basically what we show is that, so there's kind of two parts. We say for the following S structures, you get a notion of S structured equivalence. So the first one is the pointed structure, which I did on an earlier slide. There's the constant structure. There's product of two structures, function space between two structures, and then maybe of some structure. And maybe is just in this grammar because it comes up in the signature of Qs. Of course, you could keep going, but this is kind of where we stopped. Now, so what we show is each of these has some notion of S-structured equivalence, where in the case of like product, you have to have a notion of S-structured equivalence on S and T, okay? And then that notion of S-structured equivalence is univalent. So it satisfies that, that condition that makes the SIP hold. And once again, in the case of products, you have to have a univalent notion of S-structured equivalence on S and on T. So the upshot is that if you have any kind of structure that's built out of these combinators, like the signature of a monoid or anything like that, then there is a notion of S-structured equivalence, and there is a proof that that notion is univalent.
Good, thanks. Yeah, the alpha was one of the things that confused me. So
yeah, that's
constant.
just a constant type.
Yeah. Okay.
Yeah. Okay. So we can already use the structure identity principle in this way to get proof transfer for equivalences. So I know I said it was a bad example, but I'm going to do it anyway, the binary numbers. So binary numbers are just, lists of zeros and ones without trailing zeros. And these are, of course, equivalent to the usual unary numbers. And in fact, by the SIP, we can show easily that there's an equality of monoids between the ordinary monoid on the natural numbers and the and a better one that you can define on the binary numbers, where plus sub bin is like binary natural number addition. So using the SIP, we see that if you have any property of monoids, then it holds for the natural number monoid, just in case it holds for the binary natural number monoid. Okay, that's just a simple consequence of transport. But in fact, I just want to make something clear here. In some sense, you kind of don't need the SIP, because we have an even stronger result, which is that because the natural numbers and the binary natural numbers are equivalent, just not only any monoid property, but just any property at all about natural numbers will transfer to the binary natural numbers. So if we have P some property of a natural number, we can use transport to get a property P prime about binary natural numbers, such that P holds for n exactly when P prime holds for f of n. But this isn't what you want to do. The reason why you don't want to do it is that this just kind of blindly transfers everything across this equivalence. So for example, if you were doing this in order to take advantage of a more efficient addition, well, if you transport just over the type equivalence, then the version of binary number addition that you get is defined by taking both binary numbers, converting them into unary numbers, adding them as unary numbers, then converting them into a binary number. And there's no magic here. That's just what it does. So that's clearly not what you want if you're trying to use binary numbers for the purpose of being efficient. So so you really do want to use the structure identity principle, not just univalence, if you're trying to do this kind of proof transfer trick. Now, what about for Qs? Well, okay, first of all, the carriers, the correspondence between list Qs and batch Qs is not an equivalence of carriers, so we can't get off the ground with using the structure identity principle. But in fact, the batch Qs aren't even a Q. And what I mean by that is if we wanted to impose axioms on Qs, so a natural axiom would be if a Q is not empty, then it doesn't matter if you NQ then DQ or you DQ then NQ. Okay. The batch Qs actually don't satisfy this equation. And the reason is that a DQ can cause the front to get flipped before or after you add something else to the Q. So the place, of course, you've got the same logical Q, but the kind of place where the gap is located may change depending on the order of the operations. So we can kind of fix both of these problems in a sort of simple way, which is observing that every batch Q kind of can be put into normal form, so to speak, by looking at the unique list Q that it corresponds to. And using this, we kind of get equivalence classes of batch Qs that all correspond to the same logical Q, and we can quotient by this equivalence relation. And if we do that, then we can actually check that the empty and NQ and DQ actually descend to this quotient, and that we and that we'll actually get an equivalence, and in fact a structured equivalence between the list Q and the quotiented batch Q. So that's kind of what we're going to do in the rest of this talk. But I'm not going to do that example more. I'm going to actually just move right on to a generalization of that example. But again, good time for questions. Okay, so in this case, the relationship between list queues and batch queues is a function. Going right to left, but it's a function. There's every one list queue corresponds to many batch queues. So we can improve this function into an equivalence by sort of contracting the fibers, quotienting only the right-hand side. But in the representation independence scenarios in general, the relation may not be one-to-many or may not be a function. It may be just many-to-many. And the reason is that that often, well, we don't usually phrase representation independence in the presence of hits. And for many types, there may be no sort of non-hit representation of the data structure that has normal forms. So what I mean by that is that the list queues here kind of correspond, the equality on list queues is the logical equality of queues, but there may be no way to arrange that to hold without using hits. So an example of this would be if you have finite multisets over some element type, and there's no ordering on that element type. If there were an ordering, you could just say you have to maintain the order, and then you'd have a unique form. But if there's no ordering, there's not a unique form. So just as in the batch queue example, you can kind of improve the relation, the structured relation to a structured equivalence by quotienting one side. What we're going to do is improve the structured relation to a structured equivalence by quotienting both sides. And basically the rest of what I'm going to talk about is the situations under which you can do that. So first, let me look at the first part of this problem, which is improving a relation to an equivalence just on the carriers without worrying about the structure preservation yet. Okay, so there's this kind of funny condition that comes up in the literature from time to time about parametricity, which is called zigzag completeness. And the best way to understand it is just by looking at this picture. If you have a heterogeneous relation, a binary relation between two different types, then we say that it's zigzag complete if whenever x is related to y and x prime is related to y and x prime is related to y prime, then the other part of the zigzag exists and x is related to y prime. This condition is always going to be true for relations that are the graph of equivalences. And in fact, for the graph of any function, it's always zigzag complete. Now, this condition is basically capturing some notion of symmetry and transitivity for a heterogeneous relation. So of course, you can't just say if rxy, then ryx, because that doesn't type check, but this is kind of the version of that that makes sense for a heterogeneous relation. These are sometimes called quasi-pers or quasi-partial equivalence relations because they're symmetric and transitive. So we introduced something called a quasi-equivalence relation, which is sort of a reflexive, symmetric and transitive heterogeneous relation. So a relation is a quasi-equivalence relation if it's zigzag complete, that condition on the previous slide, if it is h-prop valued, and if everything on the left is merely related to something on the right and vice versa. Okay, and these are kind of the reflexivity. Now, the significance of this definition is the lemma here, which is that that this heterogeneous relation induces homogeneous relations on A and B, where the relation on A is, two things in A are related if there's merely something on the other side that both of them are related to by R. Okay, and you can similarly define a relation on the right-hand side in the same way. And these induced relations are going to be equivalence relations on A and B if and only if R is a quasi-equivalence relation. And in fact, even better, if you have a quasi-equivalence relation, then when you quotient both sides, it actually turns into an equivalence. So what I mean by that is you get an equivalence between the two quotients such that that the equivalence sends x to y exactly when x and y are related by the relation. And to prove this equivalence, that does use effectivity of quotients, as you might expect, because you have to go from the fact that two things are related to getting a proof of the relation out. So one thing I wanted to ask everyone here was, this is kind of a mysterious thing. Well, quasi-equivalence relations are new, but these kinds of ideas are sort of mysterious folklore that comes up in CS, and I was very curious to hear if this sort of simultaneous quotienting of two things by a suitable relation is something you've seen in math before, but maybe we can discuss that afterwards. Okay, so that settles the question of when a relation can turn into an equivalence. Now, the other half of the story is, when does a structured relation turn into a structured equivalence? And mirroring the definitions in the ordinary SIP, we say that if you have two S-structured types A and B, and we have a relation between the carriers, then we define some notion of being S-structured, which I'm going to call rho. It's the same as like the iota before. Then we say that one of these notions is good, it's univalent, if there's some technical conditions I'll get to in a second, but the most important part is you can always take a relation R and you can take a notion of structured relation, I should say, rho, and you can regard it as a notion of structured equivalence. The reason is that every equivalence induces a relation just by looking at the graph. So we say that rho is univalent if, when you do that, when you just apply it to the graphs of equivalences, that what you get out is a notion of structured equivalence that is univalent in the previous sense. Now, as for these, okay, I'll get to the technical conditions in a second, but we get an analog of the theorem from before, which is that according to this grammar, the sort of natural notion of structured relation is univalent for things built up in this way. And it's more complicated this time for basically one reason. There's this positivity restriction on things that occur to the left of the arrow. So P here is like a positive structure. And pretty much this is the same grammar as before, but there are two caveats. First of all, the constant structure is only univalent for types that are H sets. And the second caveat is that you kind of can't have negative occurrences of X on the left of an arrow. So you can't have a structure that says X arrow X, arrow X. But more or less everything else is fine. And once again, we use reflection to match this grammar. And again, what I mean by this theorem is, for everything in this grammar, there is a notion of S-structured relation that is what you think it is, and also that notion is univalent. Okay, so what were those technical conditions? All right, so a notion of being S-structured, rho, is suitable if the following things hold. So first of all, the structure has to send H sets to H sets, and this notion of structuredness has to be an H prop if you hand it an H prop valued relation. This notion rho also has to be symmetric and transitive in the sense that if R is an S-structured relation between A and B, according to rho, then R inverse has to be an S-structured relation between B and A, according to rho. Okay. Similarly, it has to be transitive. So if R is an S-structured relation from A to B, and R prime is an S-structured relation from B to C, then R composed with R prime has to be an S-structured relation between A and C. The final condition is kind of the most important one. And this is saying that the S-structure descends to the quotient. So what we say here is that if you have an S-structure, or if you have a carrier X with an S-structure S on it, and you have an S-structured equivalence relation on X, then there has to be a unique S-structure on the quotient of X by R for which the graph of the inclusion from X into X mod R is an S-structured relation between the original thing XS and the quotient structure X mod R S bar. Okay. I know that sounds a little complicated, but instead of staring at it more, maybe I'll just show you where it comes up. What we want is the following thing to be true. Yeah. So suppose we have types X and Y. We have a quasi-equivalence relation R between X and Y. Okay. We have S structures S on X and T on Y, and R is an S-structured relation between XS and YT. Okay, that's the setup. Then, well, we certainly get functions from X into X mod R left and Y, and from Y into Y mod R right. And because R is a quasi-equivalence relation, we actually get an equivalence between X mod R left and Y mod R right. Okay, that's just from the fact about quasi-equivalence before. And what we get from all these technical conditions is that the graph of the inclusion from X into the quotient of X, this, first of all, induces a structure S bar on the quotient of X. And the graph of this inclusion is an S-structured relation between S and S bar. Similarly, the quotient map for Y, the graph of that gives an S-structured relation between T and the induced T bar. And we get that S bar and T bar actually have an S-structured relation between them that's given by the graph of the induced equivalence from R between the quotients of X and Y. So a corollary of this is basically the relational version of the structure identity principle that we get. It says that if you have two S structures A and B, and you have an S-structured quasi-equivalence relation between their carriers, then each of the quotients gets an induced S structure on it, and those two induced S structures are equal as S structured types. Okay, so let me just close with an example of this. So let's look at the structure of having a finite multiset. So if X admits a structure of finite multisets of elements of alpha, then what that means is that you have an empty multiset, an element of X. You have an insertion function that, given an element of X and an element of alpha, you get a new multiset, new element of X. There's a union and there's a multiplicity or counting function. So what our theorem says is that if you have two types A and B that are implementations of finite multisets on alpha, and you have a quasi-equivalence relation R between the carriers of A and B, then to be structured is for the following four things to hold. The relation, which has to be a quasi-equivalence relation, it has to relate the empty multiset in A and the empty multiset in B. The insertion function has to preserve the relation R. The union function has to preserve the relation R. And the count function has to preserve the relation R. You can see what I mean by that, but it's exactly what you think I mean. If you prove all these things, then without proving anything else, what you immediately get is that you have an induced multiset structure on the carrier of A mod R and the carrier of B mod R. So the quotients immediately get induced multiset structures on them, by which I mean you get an insertion function, a union function, and a count function on the quotients. And those multisets are equal as elements of the type of structure types. Okay, well, I'll stop there, and I'll just to close, I'll say Well, it's nice to structure result or to transfer results between structures. It's convenient, and the structure identity principle lets you do that for structured equivalences. And in fact, in the Cubical Agda library, I think they're already using it to make some proofs easier. And what we're doing is basically establishing conditions under which structured relations, which are much weaker than structured equivalences, can be improved to structured equivalences in the sense I said before. Right, so I'll leave it at that. A link to the formalization is on this slide, and I'll take any questions. Thanks.
All right, thank you very much. So we're going to thank Carlo for this great talk. So please don't unmute. You should just hear me. And I think there were many questions that Carlo asked that people in the audience can answer. But of course, everyone is welcome to ask Carlo questions. So it really ought to be a discussion. So just feel to unmute your microphone and go for it.
I thought it was 30 minutes of me asking questions.
Well, we're actually done earlier. So we have, yeah, was it 37 if I do my addition or subtraction correctly.
Yeah,
yeah,
please.
Someone should just.
Yeah.
Okay, I'll get the ball rolling. So can you go back to the example with queues and explain how this theory would apply? Because your batch queues don't satisfy the axiom, so I'm just a little bit confused. Do you apply it to the axiom-free version of what a queue is?
Yeah, exactly. So right. So here's how it applies. So first of all, this relation that I'm picturing on the slide, it's clearly a quasi-equivalence relation, and that's because it's the graph of a function. Okay, so that part is good. I didn't prove, but one thing you can check is that this is a structured relation in the sense of preserving empty and preserving NQ and preserving DQ on the raw queue structure. Okay. Now batch queues are not batch queues are a raw queue, but they're not like a queue with axioms. But if you apply the relational SIP to these two things and this relation as the raw queue structure, okay, then all the hypotheses apply, like I was just saying. So you get a quotient of the batch queue that is equivalent as a raw queue to the list queue. Does that part make sense?
Mm-hmm. Yeah.
Okay. Then the axioms are just a HPROP valued condition on a raw queue structure. And because we have two equal raw queue structures, you can transfer the fact that they're true about the list queue to immediately just by transport, you get the axioms holding for the equal structure on the quotiented batch queues. Mm-hmm. Therefore, if you pair the quotiented batch queue with the transported proof that the axioms are satisfied for the quotient, then you get a queue with axioms on the quotient. Does that make sense?
Yeah. So this isn't exactly related, but what happens then with your example, say with machine integers and natural numbers, where they aren't even equivalent? I'm only asking because you did mention that example as an important one.
Well, here they're not equivalent either. Maybe.
Okay, but I mean, are you thinking you would then quotient the natural numbers to match machine integers? Is that?
Yeah, exactly. So
Okay.
it would be like natural numbers mod 2 to the 64. Yeah.
Right. Okay.
Right. So then what you would have to check. So we didn't do that. I mean, to be clear, but basically then the idea would be you would have to check that all the computations that you're doing, are not wrapping around. And if they're not, then they of course work on the quotient equally well, right? So I think in part of the point, maybe just to zoom out, I mean, you could say, well, I can always sort of quotient things by enough stuff that that some equation is true. But kind of the point is that you kind of get the result that you want, and also you can't just quotient by any old thing, or else you certainly wouldn't get the structure descending to the quotient, if you quotient by too much. So so the fact that that holds is kind of saying that yeah, that you're getting the right thing in some sense.
Thanks.
I have a question. These relations that respect the structure look very co-inductive to me.
Sorry. Oh, okay.
I guess I'm not thinking about the case of the cues that you started with. I don't know, like.
Oh, I see. I see what you're saying.
It feels kind of like you're saying that the cues are this here, yeah.
Yeah.
That's like that these are like destructors of a co-inductive type somehow, and you're constructing a bisimulation. Is there any? Can you get any mileage out of that?
Yeah, no, that's a great question. That is kind of how we think about it, because in terms of observational equivalence, I said I wouldn't talk about it, but kind of the reason why we think of this being true in like normal programming languages is that the only observations you can make on a Q are via these sort of projection functions, the NQ and DQ. And because those are sort of the only observations you can make, as long as the whatever the secret internal representation is sort of preserving the simulation, there's a sort of simulation between the two representations, then all of the observations can't tell the difference. So that's definitely kind of how we think about it in that context. I'm not exactly sure how to connect that with what I was saying today, but no, that is a good question.
Okay, any more questions? I'll wait a bit, just in case. Oh, goodness.
All right, I'll ask another question. This issue that you brought up of the fact that you don't want to just transport addition of unary naturals over to binary naturals is something that came up in a conversation on Zulip, I think, about uses of univalence. Does that mean? I guess that means that when you have multiple representations of an interface, that you need to of course you need to separately implement all of your basic operations on them, and then prove that these implementations correspond. So I guess maybe the question is, how much work do you actually get saved? Is this only useful for transferring properties back and forth, or is there ever any sort of situation where you would transfer some structure or operations?
Right. So I mean, you can definitely, I think it's useful to transfer sort of derived operations. You have to decide basically, this also just comes up in PL all the time, where you decide what things do I want to expose as part of the interface, right? And you want to choose those in such a way that, well, really one of the main criteria is that anything that you can't implement efficiently without, or anything that you can't implement efficiently without poking into the internals of the representation, that's something you want to expose directly, because if you don't expose it in an efficient way, you'll never be able to implement it in an efficient way using the rest of the exposed operations, right? So so I think you could make a case, for example, like you definitely want to expose the addition there, because otherwise you're not Like if you're just exposing 0 and successor, you're not like getting any mileage over out of using, you know, out of using binary numbers. But it might be that if you're, but if you have, if you expose addition, then, you know, the fact that you don't expose multiplication is not too big of a deal or something like that. I mean, it depends on what you're trying to do, but, and then as to how difficult it is, so basically the way that I think of the SIP is that it's just a way of making it much easier to prove that the, that you have this equality of monoids. Right. And you could do it without, because this is just some sigma types. You can just ask the question, you know, what does it mean to be equal in the sigma type? But then you run into all these like, you know, transports and path overs. I mean, even in cubical type theory, proving that two things are equal in some like, you know, tenery sigma is not like easy. So it's basically combined with the sort of automation, the light automation that we have, it's really a way of decomposing this sort of more complicated equality into a bunch of very simple conditions you can check, like the conditions I had on the multiset. You just have to check, you know, it relates the empty things. It's preserved by NQ, it's preserved by DQ, et cetera. Things you would expect to have to check. And the more things you add to the interface, the more that you have to check, of course. But yeah, I think you can evolve the code over time, and you can, if you find you need something else to be added to the interface, you can do that. Maybe this is a good time to actually plug some of the work in the univalent parametricity paper. So one of the things that they do is they describe something called the anticipation problem. So basically the problem is, if you were formalizing some fact about natural numbers, you were probably doing it just over the natural numbers, not over an arbitrary monoid, right? So you're probably in this sort of latter situation here, not in the former situation here. But what they did is they put together a whole bunch of like, I don't know, type class magic in Coq that basically tries to lift something that's stated specifically to something that's stated generally with respect to an interface. So it kind of tries to abstract away, you know, from nat to monoid or things like that. Of course, this is not like a perfect thing that you can always do, but they, you know, they developed a bunch of machinery to make that work better. And so we didn't do any of that, but I think it's kind of orthogonal to, you know, what I'm talking about. So you could imagine designing some machinery that makes it easier to kind of suck up some proof that was not written in a fully abstract way and making it more abstract after the fact. And then using that, you can apply the SIP, you know, more fruitfully. Right?
Okay, anyone else wants to ask a question or plug anything else? That's what shows are for.
Yeah, well, I'll ask a question.
I have a.
Yeah, no, go ahead, please.
Can you explain about strict positivity condition in your theorem? So what goes wrong if we drop strict positivity?
That is a great question. So the problem is pretty simple. It's that that the structure does not descend to the quotient. So imagine, so what we want is you have a structure that takes a higher order function like this on the carrier, and you are trying to get the same structure, but instead of being on X, you're trying to get it on X mod R. But so what that means is you have to be able to take a function X mod R, arrow X mod R, arrow X mod R, or you have to create one of those things from a function that goes X arrow X, arrow X. And you can't do that, basically. If you only have a function on the quotients, you can't sort of undo it to get a function on the, you know, from X to X, from a function X mod R to X mod R. So it's this sort of last condition that that you're not able to do. So it really is kind of like the idea of descending, yeah, of getting the induced structure on the quotient just doesn't work for the sort of negative occurrences. But yeah, so my question is basically not just have you ever seen a zigzag before, because I know you've seen zigzags before, but it's have you ever kind of seen the situation where you want to quotient where you're not quotienting one thing by an equivalence relation. You're kind of quotienting two things at the same time by some sort of equivalence relation between them and improving that into an equivalence. That's kind of my question.
The only thing I can think of is a situation of many object equivalence relations in topos theory or regular categories or something where there you're not quotienting the two objects separately, but it's like you have one equivalence relation on more than one object at a time and you quotient them all together. That's not exactly the same though.
Okay.
I was going to observe similarly that doing category comparisons with respect to another category is a possibility. And I'm sure Mike knows more about this than I do, so I'll stop there.
Okay, yeah, thanks for the link. I'll definitely check that out. Yeah, like I said, this is the quasi-pers are something that kind of come up from time to time, and it's sort of the right condition, but it's not something I've seen in other contexts. So, one difference, of course, is that here it has to be reflexive, and so the significance of that is that usually, like if you're implementing data structures in ML, you might have a representation that's like a balanced tree, but your type system might not be strong enough to say balanced. So instead you define the carrier as just like all trees, but you just maintain an invariant that it's balanced. So it's important that that you have a representation type or a carrier for which not everything in the carrier is actually reachable using the operations. But here, since we're using dependent types, you can kind of always cut down to just the reachable things. In fact, you probably want to. Say balanced tree, not just arbitrary tree. And so in that sense, because we're in dependent type theory, it's not really a big deal to ask for it to be reflexive in the sense of kind of everything in the carrier being real. And you kind of want that anyway, because that way you can improve it into an equivalence. Otherwise, there would be things on one side that are being missed by this function.
All right, anything else? If anyone can think of any examples, I would remind everyone that we have a mailing list where the announcements are sent, so feel free to continue. That sounds like something like we all should have seen it somewhere as mathematicians, and I'm kind of shocked that it's so hard to think of an example. Anyway, any other questions or comments before we wrap up? Okay, in that case, let's thank Carlo again. And that's it for today. HoTT will resume in 2 weeks, March 11th, with Andrea Vizzozzi.